you for joining us for Module 3, PowerPoint questions. In this video, we will review how to answer the questions. Question 1 asks us how many moles of magnesium are present in 87.3 grams of magnesium. This is a simple grams to moles conversion. So we start with our given, 87.3 grams. We multiply that by 1 mole over 24.30 grams, which was the atomic mass of magnesium on the periodic table. We do our division, we get 3.59 moles. Number 2, calculate the number of grams of lead in 12.4 moles of lead. Similarly, this is going to be a grams to moles conversion. So we start with 12.4 moles. We look up lead on the periodic table. Of course, it's a heavier element, so we find it is 207.2 grams per mole. We do our multiplication here, and we find out that we have an awful lot of grams. $2,569. That's too many digits for our significant figures here. So 2,570 grams of lead. We move on to 3. 3 asks us how many particles, how many atoms are in 15.6 grams of silver. We don't have anything that goes directly from atoms to grams, so we know that this is going to be a multi-step conversion in our dimensional analysis. We take 15.6 grams of silver, our given. The first thing we need to do is eliminate grams and convert it to moles. So we find it on the periodic table, and we get the atomic mass of silver, 107.87 grams per mole. And then we use Avogadro's number to get rid of moles. 1 mole has 6.022 times 10 to the 23rd particles, in this case atoms. You'll do your multiplication and then division, and you'll find your solution. Do be careful of significant figures there. Number 4, we're looking at the molecular mass of ammonium sulfate, NH4 2SO4. So to find molecular mass, we need to account for every atom that is in the molecular formula. We find there are 2 nitrogens, 8 hydrogens, 1 sulfur, and 4 oxygens. We use the periodic table to find the atomic mass for each of those. For nitrogen, 14.01, 1.01 for hydrogen, 32.06 for sulfur, and 16.00 for oxygen. Then we multiply for each. And obviously I just multiplied incorrectly, but 2 times 14 would be 28.02. And then 8 times our 1.01 for hydrogen would give us 8.08. Our 32.06 carries over. And 4 times 16.00 is 64.00. Add those together, and that's going to give you your molecular mass. Because we're looking at molecular mass, remember we're in AMUs, we're not looking at moles. So we're not looking at grams. Number 5, how many hydrogen atoms are in 72.5 grams? Apologies for the capital G there. It didn't transfer over nicely. of C3H8O. So we started out with 72.5 grams. We're going to multiply that by 1 mole over the molecular weight of C3H8O isopropyl alcohol. And then we'll convert into individual atoms. We're looking for hydrogen here, so we need one more step. We're going to use the mole ratio of 1 mole of isopropyl alcohol has 8 hydrogen atoms. So we'll come back to that. Let's go ahead and get the molecular mass of C3H8O isopropyl alcohol. We know that we have 3 carbons at 12.01. We have 8 hydrogens at 1.01. And we have 1 oxygen at 16.00. We'll add those together. We're going to get 36.03 plus 8.08 plus 16.00. And you get 60.11. So know that 1 mole of isopropyl alcohol is 60.11 grams. So far we are given grams of C3H8O. 1 mole of C3H8O has 8 hydrogen atoms in it. So our ratio there is 1 mole of C3H8O to 8 moles of H, hydrogen. Do your multiplication and your division. Just double checking here, we've eliminated all of our units to make sure we're going to end up in the correct unit that we want. We look good to go. Moving on to 6. An unknown sample is found to contain 75.69% carbon, 8.80% hydrogen, and 15.51% oxygen. What is the empirical formula for the compound? So we can assume here that we have a 100-gram sample. And so of that 100 grams, 75.69 grams would be carbon. So this is just converting into moles. We look up our atomic weight for each of these. Carbon was 12.01, hydrogen was 1.01, and oxygen is 16.00 grams per mole. So we begin doing our unit conversions here. 75.69 divided by 12.01. And we get 6.30 moles. Next we get roughly 8.71 moles. And then finally 15.51 divided by 16.00 is 0.9699 moles. So these are ratios here. We're looking for an empirical formula. We divide by the least or smallest number, so 0.969 divided by 0.969. And then we take each of the other two divided by 0.969 as we find our ratios. For carbon, we get roughly 6.5. We see that for hydrogen, we're going to get roughly 8.99. And then, of course, for oxygen, we have 1. So we're going to go ahead and round here to whole numbers. We get 6.5. I can't really round that one, but I have a 9 and I have a 1, so those are nice. But I'm going to have to multiply everything by 2 to end up with a nice whole number. And so I get 13, 18, and 2. So my empirical formula is C13H18O2. Number 7, unknown sample is found to have 6.444 grams of boron and 1.803 grams of hydrogen. The molar mass of this compound is determined to be around 30 grams per mole. And again, the question didn't transfer over here properly to our slide, but we are looking for the empirical formula and the molecular formula, knowing that the molecular mass is somewhere around 30 grams per mole. So we start out just like we did prior, assuming here we had a sample with 6.444 grams of boron and 1.803 grams of hydrogen. We're first going to need to get out of grams and into moles to find our ratios of moles. And so we look up on the periodic table and we find that a mole of boron is 10.81 grams. By now you've probably memorized that 1 mole of hydrogen has 1.01 grams. And so again we are looking here for whole numbers. And so we look at figuring out our mole ratios. And we're going to take the smallest number and divide it into the larger number. And that's going to give us our ratios. And so in this case we have boron has 0.5961 moles, hydrogen has 1.789 moles. We divide each by 0.5969, and this is going to give us our ratios here. We have roughly 1 mole of boron per every 3 moles of hydrogen. So we've figured out that our empirical formula is BH3, but we're also asked to determine the molecular formula, knowing that the molecular mass is around 30 grams per mole. So we need to find the empirical formula mass, and what we do here is we take our boron, which is 10.81 grams per mole, plus our 3 hydrogens at 1.01 grams per mole each. We add them together. We get 13.84 grams per mole. We know that the molecular mass is somewhere around 30, so we take 30 grams per mole, divide it by our 13.84 grams per mole. We get 2.16, and this is close enough to 2, so we're going to distribute our 2 back across our empirical formula. We're going to get B2H6. We could multiply that, and we're getting again just by the masses of boron and hydrogen, and we're going to get again close to 30. And it doesn't say it's exactly 30, it says close to, and you'll notice that it only has one significant figure in that number since there was no decimal. So we look to be good there. Number 8, an unknown compound is found to have 75.46% carbon, 4.43% hydrogen, and 20.10% oxygen by mass. The molecular weight is 318.31 grams per mole. What is the molecular formula of this compound? This is very similar to what we've just done. We're going to assume a 100-gram sample. And so we'll start with our given of 75.46. We're assuming here grams of the sample is carbon. We convert to moles. Do the same thing for hydrogen at 4.43%. We're changing it to grams of our 100-gram sample. And then we do the same thing for oxygen, 20.1%, or 20.10 grams of our 100-gram sample will be oxygen. So we look up on the periodic table, we find the respective atomic weight, and then we multiply across here to find how many moles we're dealing with. In our sample we have roughly 6.28 moles of carbon, 4.39 moles of hydrogen, and 1.256 moles of oxygen. Now we're going to again divide each by the smallest amount of moles, and so in this case 1.256. And we're going to get our ratios here for our empirical formula. So hopefully you're doing this math with me. So we discover that we have roughly 1 mole of oxygen to every 3.5 of hydrogen to every 5 of carbon. Again, we're looking for whole numbers, so we're going to go ahead and multiply by 2 for our empirical formula. And so we get C10H7O2 . And so we determine the molecular weight, molecular mass here of C10H7O2. So we're multiplying our 10 carbons by 12.01, our 7 hydrogens by 1.01, our 2 oxygens at 16.00, and then we are adding together. And we're going to get 159.17. 318 was our given mass, 318.31 divided by our 159.17. We see that we get 2, so we distribute our 2 back across our empirical formula. And that takes us to 9. These are simply balancing equations. We have a combustion reaction here. We know it's combustion because it makes carbon dioxide and water as the only products. So we're going to start out with our given equations here, our given reactions. The easiest way to do this is just to make our I chart or T chart, and we're going to list all of the reactant elements and how many of each we have. And we do the same thing for the products and list how many of each we have. Since we cannot create or destroy matter, we have to make sure that they balance. We're given 6 carbons, 12 hydrogens, and 6 plus 2 is 8 oxygens. The reactant side, we have 1 carbon, 2 hydrogens, and 3 oxygens. Let's start out with everything but hydrogen and oxygens. We started out with carbon. We're getting it to balance on the right. So we use a coefficient of 6. Gave us 6 carbons, but also 12 plus 1 more is now 13 oxygens. We try to balance our hydrogen here with 6. That gives us 12 hydrogens, but now we have 6 oxygens plus the 12 from the carbon dioxide gives us 18 oxygens. We go back over to the reactant side. We have 6 oxygens in our C6H12O6. So we'll subtract that from the 18 on the right. We know that we need to get to 12 more. So we put a coefficient of 6 in front of oxygen, and now that gives us 18 on the left. Next, we have a synthesis reaction here. So lithium plus nitrogen gas, one of our polyatomic elements, combine to form lithium nitride. So we'll go ahead and make our chart. And when we make our chart, we see that we have 2 nitrogens on the left, 1 lithium on the left, 3 lithiums on the right, 1 nitrogen on the right. So we put a coefficient of 2. That's going to make our nitrogens balance, but now our lithium was unbalanced. It was 6 to 1, so we had a coefficient in front of lithium on the reactant side, and now we're balanced. Number 11 is decomposition. Our larger molecule falls apart. S2Cl2 becomes S8Cl2, being cognizant here of the numbers just so we continue to focus on numbers on the reactant and the product side. So we make our chart, 2 Cl's, 2 S's on the right hand side, 2 Cl's, 8 S's. So the first thing we'll look at is we want to get our sulfur to balance. So we put a coefficient of 4, that gives us 8 sulfurs, but now we also have 8 chlorines. Over on the right, we put a coefficient of 4 to get it to balance. Number 12, we are looking at a double replacement balance here. PbNO3, K and I to deal with on the reactants, PbI, K, N, and O to deal with on the product side. And so we look at our lead nitrate and our potassium iodide, and then our lead iodide and potassium nitrate. And so we start counting, and I have 1 lead, and I have 2 nitrogens and 6 oxygens, 1 potassium, 1 iodine. On the product side, 1, 1, 3, 1, 2. So again, we'll try to save O and H always until the end when we can. And so we'll start with our potassium here. We'll put a 2 in front. But now we're unbalanced over on the potassium and iodine. But a simple coefficient of 2 on potassium iodide helps us balance again. And that's going to take us to 13. And our reaction here is incomplete. It didn't quite carry over. So I'm rewriting it here for us. That's 2 vanadiums, 5 oxygens, plus calcium there. And then a calcium and an oxygen, plus a vanadium. And so we'll go ahead and balance, making our chart, listing our elements. Two vanadiums, 5 oxygens, 1 calcium over on the right hand side, 1, 1, and 1. So generally we like to save oxygen until the end. But in this case, it's going to be the one we know we're going to have to deal with. So we start here with our 5 coefficient, gives us our 5 oxygens, but now also 5 calciums. And so we also see that we have to deal with our vanadium is not balanced. Add a coefficient of 5 in front of calcium, we got to 5, and then a 2 in front of vanadium, we got to 2. Remember, when it's a combustion reaction for 14 here, we are always only producing carbon dioxide and water. And for 15, you have the question in the PowerPoint. But it asks us to consider the following reaction, and it gives us 43.9 grams of ammonia and 258 grams of oxygen gas. We are asked to determine the limiting reactant to determine how much NO2 will be produced. So we take a look at our equation first. And we know it is not balanced. So the first thing we need to do is balance our equation. Should be NHO, not NH3. NH and O, NH and O. So I have 1, 3, and 2. And then I have 1, 2, and 3 respectively. So when we have a 3 and a 2 on opposite sides, we usually need to use those as least common multiples. And so in this case, we'll start with a 3 in front of the H2O. That's going to give us 6 hydrogens. 3 oxygens plus 2 more gives us 5. On the reactant side, I'll use 2. That's going to give me 2 nitrogens and 6 hydrogens. And so now I'm going to look at putting a 2 in front of NO2. And so now I'm looking at 4 plus 3 is 5, 6, 7 oxygens. So looking at this, I'm not going to get to a nice pretty number with O2 there. So most likely now I know that I need to look into doubling all of these. Coefficients. And so when I double all the coefficients, I get to 4 NH3. On the product side, I get to 4 NO2, and I get to 6 H2O. And that helps me now know that I need to put a 7 in front of oxygen on the reactant side. So 4, 7, 4, 3 are my coefficients. And I'll rewrite that here. So here's my balanced equation. 4NH3 plus 7O2 reacts to form 4NO2 plus 6H2O. Give ourselves a little bit more room to work here. So I need to determine which one is my limiting reactant. Is it the ammonia or is it the oxygen? And so the first thing we need to do is get out of grams and into moles. You're already good at this, you can probably fast forward. Put 43.9 grams of NH3 times 1 mole over the formula weight here of ammonia. So I find 14.01 for nitrogen and 1.01 for hydrogen. Gives me 17.04 grams. Do your division there. And hopefully you have an answer of moles. And hopefully it's somewhere around 2.52 moles. We do the same thing for oxygen. 258 grams of oxygen times 1 mole over 32.0 grams. Remember, it's O2. So you'll do your division here. Hopefully you're doing the math along with me, especially in case I make a mistake. But we get 8.06 moles. Next thing we're going to do is divide by our mole ratio. I needed 4 of the NH3. I needed 7 of the O2. Whichever one here is the smaller number is the one that I run out of first. And so in our case here, I have 0.63 NH3 as our ratio versus 1.15 of the O2 for that ratio. So I'm going to run out of ammonia before I run out of oxygen. I'm going to have excess oxygen. So now that I know that I'm going to run out of ammonia first, that's going to allow me to use that to determine how much product we make, our NO2. So I erased more than was necessary, but this is going to help us run our equation more clearly here. I start with my 43.9 grams of NH3, and again our next move is going to be to convert that into moles, and so I am setting up the ratio of getting out of grams and into moles. 1 mole of ammonia is 17.04 grams. And the next thing I do is I want to get rid of moles ammonia because I'm looking for NO2. And so I go back to the balanced equation and I use the mole ratio of 4 moles of NH3 to every 4 moles of NO2. And now this is going to tell me how many moles I produce of NO2. And I produce 2.58 moles of NO2. Now it doesn't ask me to specify here in how much grams are produced, so this is sufficient, but obviously I could then continue. But we do need to also determine how much reactant is left. And so we know that we had excess oxygen. When we reacted our 2.58 moles of ammonia, we left over quite a bit of oxygen. So here we'll take a look at that. Again, we'll start out similarly, 43.9 grams of ammonia. We'll convert that to moles. And so we have converted with moles using our molecular mass again. The next thing we do is we use our molar ratios from the balanced equations, 4 moles of NH3 to 7 moles of O2. And this is going to tell us how many moles of O2 were used in the reaction. And again, we are making sure that we're crossing out all of the units that we don't want, so we did end up with moles of O2. In this case, we have used 4.42 moles of O2. That's how many we needed, how many we used. We were given a sample of 258 grams. We want to convert how many moles we started out with. So it's 32.0 grams per 1 mole of O2. We already did this math earlier, but we'll do it again here. And so we had 8.06 moles. We used 4.42 moles of O2, so we subtract the 2. And this lets us know how many moles were left unreacted. Of course, we could convert that into grams as well if we needed to, but that answer is sufficient. Looking at 16, we're considering the following reaction here with 4.73 grams of magnesium reacting with 1.85 grams of H2O. We look at the reaction, we notice that the reaction was balanced. And so we're going to convert these sample sizes into moles. And so our formula weight for water there was 18.02. And the atomic weight for magnesium was 24.31 grams per mole. So we're going to figure out how many moles of each we have, and then we will determine our limiting reactant. We have 0.195 moles of magnesium. We have 0.102 moles of H2O. And so now we need to consider our molar ratios. Going back to our balanced equation, there was 1 mole of magnesium needed and 2 moles of H2O needed. So our sample of 0.195 over 1 mole of Mg, and our sample of 0.102 moles of H2O over 2 moles needed for H2O. Remember, the smaller number is your limiting reactant. So in this case, we run out of water first. And so now that we know that H2O is our limiting reactant, we can determine how much of our product, H2, is made. So I know that I'm starting out with 0.102 moles of H2O. I'm going to convert that, and I'm going to use my molar ratios. I needed 2 moles of H2O to produce 1 mole of H2 according to our balanced equation up there. I multiply that into grams. So there are 2.02 grams per 1 mole of H2. And this is going to give me how many grams of H2 are produced. So hopefully you're doing that calculation. 0.102 moles of H2O divided by 2 moles of H2O multiplied by 2.02 grams per mole of H2. And you should get roughly 0.103 grams of H2 being produced. Next up is 17. 17 has us considering 7.9 grams of SO3 are produced when 5.0 grams of O2 are reacted with 6.0 grams of S. What's the percent yield of SO3 in the experiment? Remember, percent yield is the percentage that your actual production is versus the theoretical production. We'll never reach 100%. We'll never react all reactants to create the full amount of product. So we'll always have a percent yield of efficiency. So we do, the first thing that we're going to do here is take a look at our equation. It is not balanced, so we're going to go ahead and balance our equation. You're familiar with this already from earlier. So we end up with a coefficient of 2 on the right. And that's going to give us 2s plus 3O2 becomes 2SO3. And so we go back to our sample that we were given here. We don't know yet which one is the limiting reactant. We know that our product here is 7.9 grams of SO3. Just some quick math showed us that we had 0.0987 moles of SO3 produced. So we go back to our limiting reactant. Here we have 5.0 grams of O2 times 32.0 grams per mole gives us 1.56 moles are present in our reactant of O2. Next thing we need to do is look at our other reactant, and our other reactant being sulfur, and we are given 6.0 grams of sulfur. And so of course we do need to convert that into moles. And so we'll take our 6.0 grams of sulfur times 1 mole and sulfur is fairly heavy at 32.06 grams per mole. And so we see that we have 0.187 moles present as a reactant. So now we're going to look at our balanced equation again and divide by our mole ratio. We needed 3 moles of O2. We needed 2 moles of S. Remember, the smaller number is our limiting reactant here. Hopefully you're doing the math as well. .094 on the sulfur. And obviously we're going to have a much smaller number for the O2, 0.052. And so we are going to run out of oxygen first. So oxygen is our limiting reactant. And so everything else now that we're doing in this equation, determining the percent yield, is going to be based on knowing that 5.0 grams of oxygen is our limiting reactant. So what we're going to do is calculate the theoretical yield and determine how much SO3 we could actually produce in perfect ideal conditions, which never happens, given that we're starting with 5.0 grams of oxygen and excess sulfur. So we'll take our 5.0 grams of O2. Let's go ahead and convert that into moles, even though we've already done that. And then we are trying to get to our product here. So we're going to set up our mole ratio. We need 3 moles of O2 per 2 moles of SO3, according to the balanced equation. So not enough to just finish in moles here, so I need to convert moles of SO3 to grams. And I know I need to because I am given how many grams I actually did produce. So I'm looking at my theoretical amount of grams I could have produced. Add up sulfur and 3 oxygens. Now let's go ahead and do our multiplication and division. We get 8.34 grams of SO3 is what we theoretically could have produced. Remember, we only actually produced 6.0 grams. And so I take actual over theoretical. Pardon me, I kept saying 6.0 grams were produced, but it's clearly 7.9 grams of SO3 were produced. And so my actual is 7.9 grams SO3 over my theoretical 8.34 grams of SO3 times 100 gives me 95% yield. Takes us to 18. Which means we're almost there. In one process, 1.54 times 10 to the third grams of V2O5 reacts with 1.96 times 10 to the third grams calcium. Calculate the theoretical yield of V and the percent yield of V, given that your actual yield of V is 803 grams. So there's a few things going on here. We've already balanced the equation earlier. We'll come back to that again here in just a moment. So let's go ahead and take it out of scientific notation there. 1,540 grams of V2O5 reacts with 1,960 grams of calcium. We need to take a look at our balanced equation, and we need to convert each of these samples into moles. And so you can refer back to earlier questions and find the balanced equation, or we can practice it again here. We'll go ahead and practice it again here real quick. Reactants, 2 V's, 5 O's, 1 calcium. Products, 1 V, 1 O, 1 calcium. We generally like to save oxygen and hydrogen for last, but it's going to make the most sense here to use our 5 to balance out the O. So our coefficient of 5 now created 5 calciums as well. I go to the reactant side, I have 5 calciums now. Balance the product side for vanadium, and I've got 2. So we're good to go here. 1 to 5 to 2 to 5. Give ourselves some more workspace here, so I'm going to erase this chart. So we have our balanced equation. Let's go ahead now and look at our samples in grams. We're going to go ahead and convert those to moles. go ahead and take your periodic table. Vanadium's not very common, so that's one we're going to have to look up here. Remember, we have two of them. It's a transition metal. And so it's relatively heavy here. 2 vanadiums, 50.94 grams per mole. And our 5 oxygens at 16.00 grams per mole. Remember to add the two together. So you get 2 times 50.94. You're going to add the 5 times 16, or 80. And you get 181.88 grams per mole for our vanadium oxide there. We do the same thing over on the other side with calcium. We look up calcium on the periodic table. And again, it's relatively heavy compared to most of the other ones we've dealt with so far. And we see it is 40.08 grams per mole. So we calculate here our number of moles that are present as reactants. We have 8.47 moles of vanadium oxide, and we have 48.9 moles of calcium. But now we must use our molar ratios. We need just 1 mole of V2O5 according to our balanced equation. We need 5 moles though of calcium. Remember, the smaller number here is going to end up being our limiting reactant. 8.47 divided by 1 is still 8.47. 48.9 divided by 5 is 9.78. So we end up with the smaller number being V2O5. That's our limiting reactant. So we are going to calculate our theoretical yield and then our percent yield based off of the fact that V2O5 is going to be our limiting reactant, and it will be making the rest of the answers dependent upon that. Probably didn't need to erase 181 there, but so be it. So if you missed it there, you'll have to go ahead and add V2O5 again to get the formula mass for that in grams per mole. And so as we set this up, remember we're trying to determine how much of our product, or V vanadium, is made theoretically. We are given our sample of V2O5, and so we are converting from the grams to moles of V2O5. So now moles is the unit that is left. Now we need to use our molar ratio. According to the balanced equation, 1 mole of V2O5 is going to produce 2 moles of V, vanadium. And so now I would have my answer in moles of V, but I need grams because I'm looking for the theoretical yield in grams. So 1 mole of V has a mass of 50.99 grams, or 94 grams. And so now I'm going to do my multiplication across, and then my division. And you'll notice that I put those in the wrong spot there. I would not have been able to cancel out moles and be left with grams. So apologies there as I switch that around. And so now my moles cancel out and I will be left with grams. So let's go ahead and multiply across and then divide. And we get that theoretically I could have constructed 863 grams of V in theory here, but it tells me that my actual is 803 grams, so my actual goes over my theoretical times 100, and it's going to give me the percent yield. And so I have a 93.0% yield. One more tough one, and then it gets a little bit easier here for the last couple. This time it tells me lead-2 carbonate decomposes. It gives lead-2 oxide and carbon dioxide. It says the reaction yield is 95.7%. How many grams of lead-2 oxide are produced? When my sample is 2.5 grams of lead-2 carbonate. So I'm going to start out with my 2.50 grams of lead-2 carbonate. That's my given. I'm going to go ahead and convert that into moles. So we need to look up Pb, C, and O3. I'm just going to take a quick peek at the equation. The equation is balanced, so we're good to keep going here. Lead has a mass of 207.2 grams per mole, carbon 12.01, and oxygen of 16.0. But I've made a mistake. Okay, if you are paying attention to this video, you're going to note that there is a math error right here. I listed O as 16.00, which is true, but I should have 3 of them, and so it should have been 48. And so while the rest of this is set up correctly, the math is incorrect. And that's going to throw off the rest of the math, but you should be able to put in the correct numbers. And so note that 1 mole of lead-2 carbonate is not 235.21 grams. You're going to need to calculate that to the correct one. 16 oxygen should have read as 48. But it still is true that 1 mole of PbO in the balanced equation gets produced from every mole of PbCO3. And then the next thing that I do is I multiply that to get it into grams. 1 mole of PbO has a mass of 223.2 grams. And so I multiply across, divide by the bottom with the correct number, which would not give me a product here of 2.37 grams. So note that I made a math error there. You'll have to put in the correct numbers. Hopefully you're paying attention. And then remembering that our actual over our theoretical is equal to percent yield. In the prompt here, they gave us the reaction yield of 0.957 or 95.7%. We just determined the correct theoretical yield, which was not what I wrote. You'll need to solve for actual. Moves us on here to 20. In 20, first thing we need to do is balance the equation. I've taken the liberty to do that. We need to complete the reaction of, or the complete reaction of 57.4 grams of CaC2 requires consumption of how many grams of H2O? So we start with our given, 57.4 grams of CaC2. We find the formula mass for that. 1 mole is equal to, add calcium and 2 carbons. We have roughly 64.09 grams per mole. I am converting this to moles first, so I can get our molar ratio here. I refer back to the balanced equation, and I see that for every 1 mole of CaC2, I need 2 moles of H2O. And I'm looking for grams of H2O, so I need to carry this one step further. 1 mole of H2O has the mass of 18.02 grams per mole. Multiply across, divide by the bottom. So it requires 32.3 grams of H2O to react with 57.4 grams of CaC2. Next, it takes us to 21. And a hormone secreted into the bloodstream in times of danger or stress contains 56.79% carbon, 6.56% hydrogen, and 28.30% oxygen, and 8.28% nitrogen by mass. So again, this is where we're going to assume our 100-gram sample. So we'll convert each of these into moles. This is similar to much earlier. I'm looking for my molecular formula. And so first I'm going to create the empirical formula based on these mole ratios. And then I'll take the empirical formula and divide that into our rough estimate here that only has 2 significant figures. Of molecular weight. So I've set up our problem here. We're at 56.79%, or in a 100-gram sample, 56.79 grams of carbon is 1 mole over 12.01 grams. Hydrogen, 6.56 grams times 1 mole over 1.01 grams. And then my oxygen was 28.30 grams, and my nitrogen was 8.28 grams. So I do my math to convert to grams here. And I find out that I have 0.591 moles of nitrogen. 1.76, 1.769 in this case, grams of oxygen, since they give me 4 significant figures. And 6.50 moles of hydrogen. And 4.729 moles of carbon. So now I need to find my mole ratio by dividing each by the smallest number, which in this case was 0.591 for nitrogen. I get 1, I get roughly 3. 6.5 divided by 0.591 gives me roughly 11. And this gives me 8. So 8 to 11 to 3 to 1. So our empirical formula here is C8H11 O3 and N1. But I need to find the molecular formula. So I need to determine the empirical mass, since I am given the molecular weight or the molecular mass. So I'm going to add up 8 carbons plus 11 hydrogens plus 3 oxygens and 1 nitrogen. And you'll see I've made a math error right here under the oxygen. And so if you are following along and paying attention, you're going to catch that. And you'll see at the end why my math is wrong, but the final answer is going to be correct. So 8 times 12.01 gave us roughly 96 here. 11 times 1.01 gave us 11. 3 times 16 would have given us 48, but I've written 36. And 1 nitrogen would have been roughly 14. So if I add those together, it would have given me, the correct answer would have given me plus 12 more than 157. But it still gives me a rough estimate of approximately 1. And so my empirical formula is going to be the same as my molecular formula. C8H11O3N. And so that takes us to 22. When benzene reacts with bromine, bromobenzene is obtained. We look at our equation. I've taken the liberty here to balance the equation for us. A 30-gram sample of benzene reacts with 65 grams of bromine. What is the theoretical yield? So since they want our theoretical yield, of course the first thing we need to do is determine limiting reactant. So we need to convert to moles. Finding our formula mass here, 78.12 grams per moles for C6H6, or benzene. we have roughly 0.384 moles. We need to determine how many moles of bromine we are given so that we can determine their ratios and which one is the limiting reactant. So we're given 65 grams of bromine being diatomic here. And so we have roughly 0.406 moles of bromine. Now when you do our mole ratios, it takes 1 mole of benzene. On the flip side, it takes 3 moles of bromine. And remember that the smaller number that results here will end up as our limiting reactant. We're going to run out of it first. And it looks pretty obvious already that bromine is going to be our limiting reactant. And so we carry on here to figure out our theoretical yield. Everything is based on the limiting reactant, 65.0 grams of bromine. Let's go ahead and convert that to moles. But then we want to know how much product is being produced here for bromobenzene. So we take our 3 moles of bromine back to our balanced equation. It's only 1 mole of bromobenzene, so C6H5Br5. And so that's going to tell us how many moles, but we need to get this back into grams. Because part B is going to ask us about grams of bromobenzene. So we have 6 times 12.01 carbons, 5 times 1.01 hydrogens, and 5 times 79.90 bromines. This is obviously a pretty heavy compound here. And so you're probably doing the math quicker than I am. We get 476.61 grams per mole of bromobenzene. Multiply across, and then divide. And this is going to give us our theoretical yield. In theory, how much could we produce if every single one of those molecules reacted? you get 64.5 grams of bromobenzene. Part B, though, tells us that the actual yield is only 42.3 grams. Remember, actual over theoretical gives you percent yield. And so actual over theoretical. That'll give you your percent yield. And congratulations, you're done.